Hello everyone, this is Madhukar from 3rd year ECE NIT AP. I will be explaining IIR filter design using Impulse Invariance method. Impulse invariance is a technique for designing IIR filters from analog filter specifications, in which the time domain impulse response of the analog filter is sampled to produce the impulse response of the digital filter. In Impulse Invariance method, we map each pole on the S-plane for the analog filter's transfer function h of s to a pole on the Z-plane of the IIR filter's transfer function h of z. This method is helpful when an analog filter is band limited such that the digital filter frequency response is closely matched to the frequency response of an analog filter. IIR filter design using the impulse invariance method are susceptible to aliasing problem because the practical analog filters cannot be perfectly band limited. To design an IIR filter having an impulse response h of n as the sampled version of the impulse response of an analog filter ha of t, h of n is ts into ha of nts, where ts is a sampling time interval. Frequency response of digital filter and analog filter is related by the equation h of e power j omega is summation of k is minus infinity to infinity ha of j omega by ts plus j into 2 pi k by ts. If the continuous time filter is band limited, that is ha of j capital omega is 0, where mod of capital omega is greater than or equals to pi by ts, and h of e power j omega is ha of j omega by ts, where mod of small omega is less than or equals to pi. In later course of the video, we will be deriving an equation between small omega and capital omega, as small omega is capital omega by ts, such that we can map the analog filter transfer function to the digital filter transfer function. Practically designing a continuous time filter that is exactly band limited is impossible. Also, inference between successive terms in the above equation causes aliasing effect. Let us consider an analog filter with transfer function expressed in terms of partial fraction expansion. h of s is summation of k is 1 to n ak by s minus sk, where sk are poles and ak are coefficients of the transfer function. Inverse Laplace transform of h of s gives h of t equals to summation of k is 1 to n ak e power sk into t. If we sample h of t periodically at t is nts, h of n is summation of k is 1 to n ak e power sk into nts. The z transform of the above equation gives the transfer function of IIR filter as h of z is summation of k is 1 to n ak by 1 minus e power sk into ts z inverse. This is similar to the transfer function of analog filter. We can map the poles of analog filter to digital filter as 1 by s minus sk is 1 by 1 minus e power sk into ts into z inverse. That is, poles in the s plane are mapped to the pole at z equals to e power sk into ts in the z plane, where k ranges from 1 to n being the order of the filter. We know that s equals to sigma plus j omega and z in polar form is z equals to r e power j omega. Equating the two equations, we get small omega is capital omega into ts. This mapping is many to one mapping. Here is the pictorial representation of mapping of S plane onto the Z plane. In the figure 1, all the poles on the imaginary axis in the S plane are mapped onto the unit circle of the Z plane. In the figure 2, all the stable poles on the left hand side of imaginary axis in the S plane are mapped inside the unit circle of the Z plane. In the figure 3, all the unstable poles on the right hand side of imaginary axis in the S plane are mapped onto outside the unit circle of the Z plane. Let us consider a problem. Design a Butterworth IIR filter using impulse invariance method by taking sampling time interval as 1 second. Given are the digital specifications with passband edge frequency omega p is 0.2 pi and stop band edge frequency omega s is 0.4 pi. We need to convert the digital specifications into analog specifications as discussed earlier. Since the magnitude response of an analog filter is a monotonic function of frequency, the above equations will satisfy mod of h of j omega is 0 equals to 1. The attenuation in the passband is given as 0.70794 and the attenuation in the stop band is given as 0.31622. We know that Butterworth filter squared magnitude response is mod of h of j omega whole square is 1 by 1 plus capital omega by capital omega c whole power 2n. Designing an analog filter with required specifications consists of determining the parameters n and cutoff frequency omega c. Thus, considering the equality condition in the above equations and substituting it in the third equation, we get equations as follow. Solving the above equations, we get order of the filter approximately equals to 2 and the cutoff frequency omega c is 0.62906. As we round off the value of n, the analog filter will not satisfy the equation simultaneously. This allows some margin of aliasing in the digital filter. With the order of filter being n is 2, there will be 4 poles in the magnitude squared response. Let us consider the imaginary poles of analog filter s equals to j omega. We can write mod of h of j omega whole square as h of s into h conjugate of s. The complex conjugate of h of s can be written as h of minus j omega, that is h of minus s. Poles of the magnitude square response will be 1 plus s by j omega c whole power 2n is 0. Upon solving this, we get s equals to j omega c e power j into 2k plus 1 plus n into pi by 2n, where k ranges from 0 to 2n minus 1. Out of these 2n poles, there will be n poles that are stable and are the poles of transfer function h of s. For the given problem, the poles of h of s are s naught is minus 0.44481 plus j into 0.44481, s1 is minus 0.44481 minus j into 0.44481. The transfer function of analog filter will be h of s is ts into ak by product k is 0 to n minus 1 s minus sk, where the coefficient ak is product k is 0 to n minus 1 minus sk. Upon solving this, we get ak is 0.39571. Substituting this in the h of s, we get 0.39571 by s square plus 0.88962 s plus 0.39571. Considering the partial fractions of the h of s, we get h of s as this. Now mapping each of the partial fraction term in the h of s equation to the z domain, we get the transfer function of the IIR filter as 0.25435 z inverse by 1 minus 1.1572 z inverse plus 0.41081 z inverse square. Let us demonstrate the given problem in MATLAB. First, we define the passband edge frequency and stopband edge frequency, attenuation in the passband and attenuation in the stopband, attenuations in decibels, sampling time interval, omega p and omega s are defined using the equation small omega is capital omega into ts. What-out function is used to find the values of order and the cutoff frequency of analog Butterworth filter. Butter command is used to find the coefficients of the transfer function h of s. H of s is found using the command tf and the coefficients returned from the butter function. INVAR is a command used to create the IIR filter using impulse invariance method that returns numerator and denominator coefficients. H of z is found using the function t of tf and the numerator and denominator coefficients returned from the INVAR method. Now we find the magnitude frequency response of the IIR filter and plot it against the frequency. Here is the graph. Thank you.